We're now going to look and see how least squares can be used to build, tune, or fit a classifier. So the way we'll do it is it's actually pretty straightforward. What we're going to do is we're simply going to do standard least squares data fitting, where the outcome is simply going to be plus or minus 1, the number plus or minus 1. Now remember, the actual outcome is either always plus or minus 1. So we'll build a model that just targets that. That's just standard least squares data fitting. Now, of course, what that means, we're going to call that thing f tilde, not f hat. The reason we're going to call it f tilde is because what it gives you is a number. Whereas, in fact, f hat must be plus or minus 1, right? Because if you say, does the patient have the disease, you're not allowed to say, whatever, plus 0.2 or something like that. You have to say yes or no. Oh, I should add, there are methods for classification where you guess a probability of something happening, and that would indeed be a number. Okay, so the idea here is, by construction, f tilde, it should be near plus 1 when y is 1, and it should be near minus 1 when y is minus 1. So that's what we're gonna construct such a thing. And then what we're going to do is we're going to take the sign of this. Now, sign is a mathematical function that gives you, this is equal to plus 1 if f tilde of x is bigger than or equal to 0, and minus 1 if f tilde of x is less than 0. Now, what I've done here is I have broken tie, which is when f tilde of x equals 0, by calling it plus 1. But it really doesn't, I mean, you can break it the other way if you like, or randomly, it doesn't matter. And you can even sort of think of a couple of interesting things here, right? Like that you can certainly interpret when f tilde is near 1, you would say, oh, it's pretty confident it's plus 1. If it's near minus 1, it's pretty confident it's minus 1. If it's plus 0.01, it's basically saying, honestly, I don't know if it's plus 1 or minus 1, but if you force me to guess, I would guess plus 1. So, okay. What we'll do is we'll look at an example now of this, and we're going to look at a famous data set. It's the MNIST data set. It's 70,000 images of handwritten digits with some pretty bad handwriting in there too. Okay, so these are 28 by 28 images of the digits 0 to 9, and there's about 70,000, about 70,000 of them. That's been divided into a training set of 60,000 and a test set. So X is a 494 vector. It's not 28 squared, by the way, because a lot of the entries are just always 0 and therefore don't matter. And we add a constant 1. And we get the, well, there's only 493 pixels which are ever non-zero. Right, so for example, the pixel at the bottom left is always dark, so it doesn't really contribute. Okay, and what we're going to do is we're going to consider the problem of guessing whether a handwritten digit is 0 or not a 0. So it's going to be plus 1 if it's 0 and minus 1 if it's not 0. So if it's 1, 2, 3 up to 9, but plus 1 if it's 1. So we're just trying to make something that will guess if an image is a 0. That's it. Okay. So here's the training set results, and the error rate is about 1.6%. So here is the confusion matrix for that. And these were, we can check a couple of things. We can say that, oh yeah, how about that? Look at that. That the number of true zeros was about 6,000. Well, okay, that's out of 60,000. That's about 1/10. Makes sense. And of the 6,000 zeros, we got a little over 5,000 correctly. Okay. And we got 765 times it was a 0, and we said, no, it's not. Good news is that when the digit wasn't a 0, we got a whole lot of them right. And we didn't make too many errors. We didn't make too many false positives. We made 167 false positives. A false positive in this context means that there's a digit, it's not 0, but we look at it and we go, we guess it's 0. Okay. So, and overall, the error rate, which is this number plus this number divided by the total, which is 60,000, it's 1.6%. Now, when we go to the test set, which is a test set of 10,000, we get about the same error rate. And that's actually all as well, right? These these numbers here, are approximately, the same as these, scaled by 1/6. That's good. That means that we're not overfit. And what it means is we can likely just find a zero with an error rate of about 1.6% on unseen images. Okay, so, and we can guess that because the train and test are very, very close here. By the way, this sounds pretty good. It's not that good, to tell you the truth. So people are down at a lower level than that, and more advanced methods of machine learning these days, and even some of the ones that we'll be able to look at later in the class, will get you actually at or beyond human performance, right? So they'll do better than people, which is kind of cool. This one doesn't. This is just very elementary least squares classification. So a very interesting thing to do here is to look at the distribution of the values of f tilde of xi over the training set. Okay, and so this is what you get, and it's actually really cool, right? So the red ones are the ones where it was negative, meaning it was a digit 1 through 9, and the blue ones show what our value of f tilde is on the cases where it really was a 0. And remember what our classifier does this. It makes a threshold here, right at 0, and it says if you're to the right of that, we're going to consider you a positive, which means 0. And if you're to the left, we're going to consider negative, and that means you're a digit 1 to 9. Okay, so this is how that works. And you can see a lot of stuff. There's a lot of blue over here. That was our maybe disconcertingly large number of, I guess those are false negatives. That's when we say, nope, that's not a 0, but it really is. Okay, so you can see that. But you do see a beautiful separation of the two classes, and that says we're really doing something here. Which is kind of cool. So here are the coefficients in the classifier. So a bunch are 0. So on the outside here, you see a whole bunch of pixels that are like just 0. And that's because, in fact, those pixels are never 0 in the images. So they're just 0 here. But you can see all the others. You can see various things, and we can even interpret it. Like, it's kind of weird. Like, for example, the fact that these are negative says that for those pixels, having a bright spot in those pixels basically, I'm anthropomorphizing this, basically very much reduces the probability that handwritten digit is a 0. Here, there's some kind of distributed things. You can actually sort of see visually kind of an annulus here where it's kind of red, and that says pixels that land, when you have a white spot in that region, it's more likely to be a 0 than not. I mean, from some points of view, when you see this, it's hard to imagine that this really does give you like a 1.6% error rate on things you haven't seen, but it does. It's super simple. One more topic relating to classification in general, but in particular least squares classification is this. We have been using a threshold here. Let's go back a couple, of 0, right? But your eyeball might want to do something weird, like say, you know what, let's use this threshold, right? And that threshold is going to very much reduce the number of our false negatives. It's going to increase the number of our false positives. But then we'll get them kind of maybe on the same scale or something like that. So this is the idea of just switching the threshold from 0. So what we would do is we'd choose a number alpha, and we're going to say that f hat of x, that's our actual guess, like -1 or +1, is +1 if you're bigger than alpha and -1 if you're less than alpha. So alpha equals 0, we recover exactly what we had before. And alpha is called the decision threshold. I mean, for obvious reasons. Now for positive alpha, what happens is the false positive rate is, roughly speaking, when alpha is positive, you are more reticent. I am, again, anthropomorphizing. You are more reticent to guess +1. Well, that means you're going to make less false positives, because there'll be something where it's not positive. You don't know it, of course, and you'll be less likely to announce that that's a +1. But so will be the true positive rate, because also some of the ones that are true positives you'll now look at and go, yeah, it was bigger than 0, but it's not bigger than alpha, so I think it's -1. Okay, Now, when you vary alpha and you make a trade-off curve of the true positive versus the false positive rates, you get a strange thing called the receiver operating characteristic, or ROC curve. And it is drawn in other ways, but this is the basic idea. And I'll say a little bit about the history of it. It's a term from World War II, and it refers to either sonar, most likely, or radar. And so the basic idea was to try to figure out, is there an enemy ship, out at 22 kilometers in that direction, right? You'd be getting some sonar readings, and then you would just guess. I mean, that's what this is about. Okay, so that's the origin of receiver operating characteristic. But it's been taken up and it's used universally in statistics, machine learning. Everyone would know what an ROC curve is. So to give a rough idea of what an ROC curve is, or how this works, what we do here is, I have displaced, I've set alpha equals, I don't know, 0.2. And what that means is all of these I'm going to classify as +1. And that's good because they're all +1. Notice that, the red distribution down here, I'm going to have an extreme, when alpha is 0.2, I'm going to have a really low error on my on things that are negative that I think are positive. So false positives is going to be super low. On the other hand, look at all these over here. My false positive rate is going to be sorry, this is the false positive. The true positive rate is also going to be much lower. So here it is plotted where we plot alpha. And let me show you what's happening here is when you imagine, if I put a dashed curve there, that's minus 0.5. Sorry, 0.5 there. What we're doing is the total number of red points to the left tells me the number of negative ones that I correctly nail as negative. The ones to the right of that thing are errors, so this would be error. Same for the blue, except you switch the orientation. So you get curves that look like this, right? And here's 0, right? And let me remind you what you want. You want the red curve to be small, and you want the blue curve to be high, okay? And you can see here that the total error, that's the simple metric that just looks at one thing, is you can see that actually, it could argue for taking, something like what I drew, alpha equals, minus 0.3 or something like that. And that would be a good threshold for this. So this is an example of our ROC analysis. This is the kind of curve that you usually get. And this shows false positive rate. So in these curves, left is good, right? And high is good, right? So that's the best you could possibly do right there. That says that your false positive rate is 0 and your true positive rate is 1, right? When something is negative, when an example is negative, you guess it's negative always. When something is positive, you guess it's positive always. So this is an ROC curve, and it's something people would talk about and things like that. And a reasonable question would be, what value of alpha should I take, right? That is subjective. And the answer to that depends on the application, and it depends on what are the relative costs of making the two types of errors. Like what is the relative cost of a false positive versus a false negative, right? So that's kind of the idea. So, and that's not anything, no math can tell you that, right? And the data can't tell you that. That's something that has to come from the application. So if you say, we can't have too many false positives because, if there's too many false positives, after all, people are going to ignore the alarm. That's a typical thing that might happen. Or you'd say, false negatives are really bad because if we don't catch this and treat that disease, the outcome is very poor. So that would be something where a false negative would be a very bad thing, right? It could also be that you have another test that's more powerful. And all you want to do, you'd skew it towards in the conservative direction so that if it comes up positive, it doesn't mean that you are certain the person has the disease. It means let's schedule some more let's schedule some more tests and see what's happening. Okay, so let me say just a few more things about this. You will learn in other courses how to do classification like this. You probably won't see least squares classification because, in fact, there are better ways to do it, which don't involve least squares, but they're extremely similar. I think when you see those things, maybe you've already seen them, but when you see them, you'll see that they actually do work better. But they're very similar in spirit. Everything else is the same. ROC curve, everything else makes perfect sense. Actually, even the model form can be identical. So you'll see better ways to do this using other methods. That's especially true for the example with the digits, right? That those things, maybe for 5, 8 years now, there are other methods not based on least squares that give stunning results in test. Of course, I would never tell you anything about the training in testing. Those have been incredibly successful. They beat people, by the way, which is kind of weird because you think, how could a machine, I don't know, how could some crazy algorithm that looks at pixels actually beat a human being? And the answer is they do. So in fact, you might, all I'm doing here is saying this is an example of least squares. To be perfectly honest, these are not bad classifiers, right? I mean, there are worse classifiers than these. They actually work okay, is the right way to say it. And they're pretty simple. So I think that's why we've covered them. And, it's also just good for you to know about what is a classifier. And now that you know least squares, you can come up with a classifier. In other courses, you're going to learn more about more sophisticated classifiers, but this is not a bad start at all.